Hello everyone, I am Garima Singh. I am currently an undergraduate at Manipal Institute of Technology, Manipal, India. And today I will be presenting my work that was done during the IRIS-HEP fellowship during this year. So before we get started, I'd like to put up a brief introduction about the project. So our aim was to develop a floating point error estimation framework using clad, and clad is a source transformation automatic differentiation tool for C++. It is implemented as a plugin to the Clang compiler and is based on the LLVM infrastructure. The framework also aims to provide the users with the choice of multiple error estimation models and even allow them to add custom error estimation models if they wish. So, before we get started, a little bit of motivation. Why do we want to estimate these floating point errors? Why should we go out of our way to do all of this? So, I have a program here, a code snippet, and it's very simple. What we're doing is we're taking a value C, and alternatively, we're subtracting and adding a value to it. So mathematically, at the end of all of this code, we should get the solution as is on the screen. So when you evaluate that expression, equivalent mathematical expression, you get minus 50. The value of C should be minus 50 by the end of this loop. However, in reality, when you actually execute this, it's very, very different. And it changes with the rounding mode as well. So if you round to the nearest, you get a completely different answer if you were to, say, round towards 0. And you can probably tell that these answers are nowhere near the answer that we should actually be getting, which is minus 50. They're all extremely inaccurate. And you might say, okay, you know what, this is just a simple program and this might not happen in real life, but you'd actually be very surprised. So, some real life implications of a similar scenario happened back in January of 1982 in the Vancouver Stock Exchange, where what was happening was over over time, the stock value was added and removed from an index. So the sum, whenever they summed up the new values, they truncated the sum up to 3,000 times per day, which resulted in a loss of index value of about $25 per month. And this happened over 23 months. So at the end of those 23 months, their actual index value came out to be 524 US dollars. However, it should have been 1,098. So, it's pretty obvious they had a reduction of value. Uh, that was about half the actual value that they should have had. So, I think this is not just this, uh, floating point errors actually have very serious implications for, you know, for very high precision applications such as simulations. And this is actually very important for at least the high energy physics community because they also want to do high precision calculation, which is always not possible because of the finite nature of computing and hence the finite nature of floating point numbers. So now that we have some motivation, let's dive into the technical details about the project. So before I talk about the framework itself, let's go over what clad does. So what is clad? Clad is basically a source transformation automatic differentiation tool. It is implemented as a plugin to the Clang compiler. Super simple. It's just a tool that does automatic differentiation. Now, what is automatic differentiation? It's also referred to as AD. Simply speaking, automatic differentiation is a way to differentiate computer programs as you would differentiate mathematical expressions. So, for example, I have this square function. It does nothing special. It just returns the square of the input. If I were to then call clad's differentiate function on it and specify the argument with respect to which I want to differentiate the square function, the result would be something like so. So at the end, you can obviously see that the resultant from clad differentiate is actually the derivative of the input. That was the square function. So now that we know about clad and now that we know about what AD is, let's talk about FP error estimation, and here FP is floating point. So a formula to estimate the error of the floating point error in a function for most cases can be given as follows. So AF is again the absolute error in a function f. Then xi is all input and intermediate variables. So here it becomes important to also take into account the intermediate variables in a function, because we want to know the floating point error in that function. So we have to also take into account the intermediate variables. Next is machine epsilon, which is again the maximum representational error in a floating point number. So this is a number enforced by the standard, and it is machine dependent. Lastly, very obviously, delta f by delta xi is the derivative of the function f, which is also called the target function. Then this is the function we want to estimate the error in. And then delta f by delta xi is the derivative of f with respect to the intermediate variable or input variable xi. And lastly, this is a term that we don't really care about specifically in our case, but it doesn't hurt to go over it. So EL is the error due to linearization in the Taylor series expansion. So now that we know what all of these terms mean, let's look at where we get them from. So the derivative we can get from clad. As I mentioned before, clad is another tool that just does calculates derivatives. Machine epsilon, we already know since it is machine dependent and it changes for different machines. EFL, on the other hand, is a bit hard to estimate. And however, because we are talking about floating point errors, E of L isn't a really big value, so it is okay for us to ignore it. However, for nonlinear functions, for some nonlinear functions, this actually may be a significant value that may be a bit hard to ignore. But for our sake, we do not talk about this value in the future. So for us, the first part of the equation is what we want to calculate, basically. So now, what's reverse mode? So as I mentioned before, the derivative we get from clad, and more specifically, we get it from clad's reverse mode AD. So let's look over what reverse mode is actually. So imagine that you have a function f, and inside it you have different function calls. So you have a nested function. You have a function with nested function calls. So it looks something like what is on the screen. So here, as you can see, that we assign all of the nested values to an intermediate variable. So each layer is assigned to an intermediate variable, wi. And you can see that x is assigned to w0, h of x is assigned to w1, and here also x is replaced with w0. So that's how we assign each layer to an intermediate variable. Now, the forward mode AD computes the following recursive relationship, which is derivative of each intermediate expression with respect to the input. And as you can probably tell, since it calculates the derivative of each sub-expression with respect to only one variable, we cannot really use this because we need the derivative of delta, the derivative of the function with respect to each intermediate and input value. So this doesn't really work for us. If we wanted to make it work, we have to run forward mode as many times as there are intermediate and input variables in the function, which isn't really optimized. However, reverse mode AD computes the following recursive relationship, which is the derivative of the input with respect to the derivative with respect to each intermediate value. And as you can tell, this gives us the value that we need without having the added cost of running it again and again. So only one pass of reverse mode computation will get us all of the derivatives we need. So that's why we use reverse mode AD while calculating the derivatives. So now that we found out what reverse mode AD meant and what kind of formula we'll be using, let's look at what estimation with clad looks like. So we have approximate pi function here, which approximates pi. Now it doesn't do this directly, and we'll see how exactly we use this to approximate pi later in a later example. But for now, it's sufficient for us to know that this function approximates pi. Now, if we were to call clad estimate error on this function, we would get the following result. It looks, the result on the right hand side looks a bit different. As you can see, it's appended with grad because it is the gradient, and it also has a few extra parameters, which I'll get to at the end. Now you can see that there is a bunch of ellipses, which is again, for brevity, I have omitted that part of the code. However, there is some specific gradient specific code in the function as well. But now let's just look at the error estimation specific part. So you can see all of the lines highlighted in yellow, and we'll go over them. So the delta tn1 basically refers to the error in approximate pi due to the variable that the delta underscore is affixed to. So in this case, delta underscore delta underscore tn1 actually refers to the error in approximate pi due to the variable tn1. And on the RHS side, you can see that it follows the same formula that we saw in the previous slide, which is the derivative of function with respect to tn1 into the value of t1 into machine epsilon. So here underscore d underscore tn1 is again the derivative of of the function with respect to tn1. EE-REPL is a basically replicate value of tn1. Now, why this is necessary is if in case there are reassignments to tn1, we want to use the correct value of tn1. So we have to save or sort of checkpoint the value at every assignment. Since there are no reassignments here, we can just assume that EE-REPL tn1 has the value of tn1 itself. At the end, E of m is machine epsilon. So as you can see, this is the same formula that we saw before, and clad is just emitting it into the code and tuning it for each variable. So you can similarly, the next delta tmp is the same. Delta tmp refers to the error in the function because of the tmp variable, and they are just the same except for the fact that it is now for tmp. And similarly, delta E refers to the error in approximate pi contributed by E. The RHS is the same, except it is modified to, modified for E. And so that's about all the intermediate variables. So at the end, you see another line, delta Tn. And why that's there is because apart from the intermediate variables, we also need to take the derivative of the function with respect to the input variables. And here Tn is an input. So since we get the derivative of the input, the function with respect to the inputs at the very end, we have to do this at the very end. And again, here the result 0 actually signifies the derivative of f with respect to f as in approximate pi with respect to the input tn1. And at the end, you can see there is a final error, which is, again, as the name suggests, it's the final error in the approximate pi function because of all the floating point operations. And that is basically the sum of all of the delta underscore star variables that we created. So yeah, that's about it. And then since this final error is a reference, it is also an output. So that's how clad calculates the final error in a function. So now that we saw a little bit about how the error estimation in clad looks like, let's talk about why it is different from the other software that do the same thing basically, right? So firstly, since clad generates estimation code as we saw before, you can use this estimation code to generate estimates for multiple input values. So this is actually super helpful if you want to analyze the function stability, which as we will see later. And this also saves you a lot of time because you don't have to reevaluate the gradient for each input. Secondly, clad's error estimation comes off the shelf with clad. So all you have to do is clone the clad repository and just call estimate error. So you don't need to set up any complex pipelines to use it, or you don't need any other software to use it. Thirdly, clad's FP error estimation does not bind the user to a signal estimation model. So that means they can build their own models and use those to calculate estimates with. For example, consider the following custom model. So Very similar, AF means the absolute error in the function, the target function. And on the IRIS, it's a bit different. What we're trying to do is we're trying to take the derivative of a function with respect to the intermediate and input variables and multiplying it with the value, with the difference of that specific variable if it were in float and if it isn't double. So what we're trying to do is we're trying to see that if what is the error in the variable xi if we downcast it from a double to a float, basically. So again, to use this error model, the user has to put a constraint on the program that it can only have double values. But let's assume that that is the case, since this is not a standard model that we use, and again, it's custom one. So once the user has figured out a mathematical formula for the model, all they have to do is turn it into a Clang expression. Now let's talk about custom models in action. So once the conversion from the mathematical formula to the Clang expression is complete, the augmented code for that custom model will look like this. So we call clad estimate error with our custom model, and voila. Again, it's the same as the one that we saw before, but here I've just used one expression just to demonstrate it and omitted the others. But however, they are actually present in the actual gradient function that you will get. So we see that we have the same delta tn1 here. It means the same thing. However, here, as you can see, this is very similar to the formula that we proposed in the slide earlier. So yeah. Depending on the custom model that you provide, clad will generate code accordingly. So how it all comes together is clad, you pass the target function into estimate error, which is the function to estimate errors in clad. And if a custom model is provided by the user, the clad registers that custom model with its error estimation model registry. Otherwise, the built-in default model is used, which is again the one that we saw in the very beginning. Why this estimation model registry is important is because later when we want to actually generate code, we need to be able to resolve to the correct function. So if the user has provided a custom model, we may want to make sure that we are using that custom model itself, not something else. So then once clad receives the estimate error request, it transfers all the calls to the error estimation handler. The error estimation handler then, I wouldn't say it branches out. It's again not a parallel task, however it can be. It branches out and clad's gradient generation module takes over. Now what this gradient generation module does is it dispatches call to the error model, which is, as we saw before, it could be something provided by the user or it could be the built-in one. And the error model in turn takes the derivatives from the gradient generation module and returns the errors. And the errors then can be emitted into the code by the gradient generation module itself. At the very end, finally, we get, once all of this is done, once the gradient of the whole function is evaluated, we get our final result, which we saw before on the right-hand side, which was the gradient function augmented with error estimation code. So this is the basic internal sequence of events that take place when estimate error is called on a function, and yeah, that's the basic overview. Now, an interesting use case for our estimation framework, floating point estimation framework, is calculating the numerical stability of algorithms, not analyzing, sorry. So remember the approximate pi function that we had before? Now let's assume there is another function. It does the same job, it approximates pi, however it looks a bit different. So this is the function that we're going to use. Same thing, it does the absolute same thing. It is also used in conjunction with the something else, and yeah, same job, however it is just a bit different. So the background setup, so we have the approximate pi on the right hand side. Now the approximate pi function is used iteratively in code as follows. So you have this loop and then you have the count, that is the number of iterations you want to approximate pi to. So with every iteration, your guess or your approximation of pi would be more accurate. So that's the whole logic behind this. And at the end of each iteration, you get the value of pi, as you can see, that is stored in the variable pi. And approximate pi Sn is actually used to calculate pi for each iteration. So that's how approximate pi is used, and the previous approximate pi is also used in a similar manner. So now let's look at some execution results. So this was a function. This was the context in which it was used. Now, after executing this function for approximately 30 iterations, we plotted the results, and they're a bit surprising. You'd think that after each iteration, the approximation of pi should become more and more accurate. However, at the 25th iteration, post the 25th iteration, it drops to 0. So firstly, it increases to 4 and then drops to 0 suddenly. This means that this algorithm is obviously not stable, since post the 25th or even the 30th iteration, your value will be 0, right? So now let's look at what is actually happening at the 25th iteration. And this is where the floating point error estimation framework comes in. So we have both of the codes here. So to figure out what's wrong, what we can do is we can analyze the sensitivity of all the intermediate variables in approximate pi. So the sensitivity of any variable xi is given as follows. It's the derivative of the function with respect to the variable into the value of the variable. So now let's plot the sensitivity of each of the intermediate variables over 30 iterations and just see what happens. So as you can notice, E and Sn1 decrease over the number of iterations. However, TMP actually increases over the iterations. So this is pretty interesting, and this tells us that there is something wrong with DMP, because as the sensitivity increases, it means that that specific variable becomes more and more sensitive to floating point errors. So if the floating point errors become large, TMP is the variable that's going to be the most affected by it. So now let's actually analyze, let's give some rational explanation why TMP is causing this specific problem. So that's TMP right there. Now for values of E, which are close to 4, TMP becomes 0. Or for values of TMP that are closer to, Sn1 becomes 0. And if Sn1 becomes 0, so does your result. And so does the approximation of pi. So and this happens because even if the value of TMP is somewhat close to 2, it will result in catastrophic cancellation, which is another problem with floating point numbers, wherein if the numbers are very close to each other, because of truncation errors or because of the fact that they cannot be properly represented, they cancel each other out and you get 0. However, you should not have been getting 0 there. So how can we fix this? So we can fix this by rationalizing the term containing TMP. And after rationalizing, we get a stable approximate pi that looks like the following. This is the approximate pi that we've been using earlier. So now, okay, you don't have to believe me when I say it's stable. Let's look at some results. And also, let's look at the sensitivity of the variables now that we have quote-unquote fixed it. So analyzing the results of the fix. So we have the stable approximate pi here. And what we'll be doing is we'll be analyzing two things. So we'll be comparing the results of stable approximate pi with unstable approximate pi for over 30 iterations. And secondly, we'll be checking the sensitivity of all the intermediate variables in the stable approximate pi. So when we compare the results, you can see the unstable version is as it was before. However, the stable version is, well, stable, right? Because it always gives you a close estimate to pi as the iterations go on, and it does not have any sort of changes during any of the iterations. Secondly, the sensitivity, you can see that now all of the variables tn1, temp, and e are actually decreasing. So as the iterations go on, the sensitivity of each of these variables decreases, meaning that they become less and less sensitive to floating point errors. So now this is enough proof that we have in fact fixed our approximate pi algorithm, and this gives us a good idea of the stability of algorithms. So if we analyze the sensitivity of all input variables, we can say that, okay, this specific algorithm is stable, and we can also pinpoint the fault areas of the changes in stability. So as we saw, we could use CLAD's floating point error estimation framework to point out where the flaw or where the instability was coming from in a function. So that's one of the many use cases of the floating point error estimation framework. So currently, let's talk about a little bit of implementation details and the current status of the framework. So currently, one can estimate errors over different functions. This includes functions with complex substructures such as nested loops, nested function calls, multiple returns, etc. We also partially support error estimation of arrays and pointers. Input arrays is currently in progress. So to calculate the floating point error estimates of a function, one has to simply do the following. So you have to, suppose you have your function, my function, which whose error estimate you want to calculate. You just call estimate error on it, and at the end you execute it. By the end of this code snippet, FP error will contain the floating point error of your function. Secondly, we also support all types of custom models. The users have to create a shared object of their custom model. They basically have to make a library and compile it into a shared object and then pass it to clad via the command line. Clad will then register that custom model with the FP error estimation registry so that it can be used to generate code later. We also currently support a built-in Taylor approximation model, which can be used out of the box. So whenever the user calls estimate error, that is the model that we default to. We are also working on the ability to write the error data for selected variables in the target function to a specific output stream, and this will help users analyze the errors in each variables, and again do something similar to what we did before for numerical stability for algorithms. So future works include but are not limited to a more generalized error estimation framework where we can see how the errors propagate through a function. So basically propagation of uncertainty using automatic differentiation. This is again super helpful for especially areas where you know that the inputs have a certain amount of error and you want to see what that error, how that error passes through a function and what kind of effects it has on the output. Secondly, lossy compression and mixed precision tuning. So what lossy compression is basically it's the task of reducing the precision of values so that your algorithm can have a lower memory footprint. And again, this reduction in precision is only done if we know that if we reduce this variable's precision, the error that this will then introduce should be lesser than a maximum specified threshold. So that's lossy compression and mixed precision tuning. Lastly is we can also utilize the error estimates via clad in root math libraries. As I said before, this is super helpful to in the area of analysis and simulation and so on and so forth, especially where you're working with a lot of floating point numbers and you need to estimate the kind of errors that you would possibly get. So that's it. You can find out more about clad at GitHub, and thank you. If you have any questions or any suggestions, please feel free to reach out to me at my email. Yeah, thank you.